this whole discussion about what is probability, what is randomness. But I want to discuss it from somewhat different angle. So I start first, indicate kind of club I don't go to. And what I'm not going to talk is philosophy and psychology of randomness, because there is lots of, partly made by mathematicians, partly by philosophers, discussing what is random and what is not random, which is not focused on any specific questions. And here, on the contrary, I want to discuss some very concrete questions, both in mathematics and outside mathematics in applications. And so, but still, first I start with a few remarks on history, but these are subjects which we shall discuss. So these are three blacks which I will not discuss, where probability concept of randomness usually, from my point of view, is just meaningless. And people discuss it and say random, like history is random, evolution is random. It's just words. There is absolutely nothing but an emotional weight attached to them, from my point of view. And because there is no specific mathematical model behind them. So my point is, whatever we speak random or whatever, you have to have in mind mathematical model, very different from the traditional one, but it must be mathematics. Any speculation, any speculative discussion without mathematics is, in my view, nonsensical. It may be preparation for mathematics, but either you have experiments or you have mathematics. Everything else is, I don't know what it is. And so the subject where, so 2 points, 3 points where mathematics is prominent and which I will discuss. One is statistical mechanics, and very similar, but in a way simply, in a way more subtle thing is formal genetics, which are not so kind of common. Then how probability applies outside of probability per se, because probability is a subject I know very little about, but I know a little bit how it works in other domains, like in geometry and in combinatorics. And then there are applications where you have to change concept of probability apparently, and these are molecular evolution as opposed to classical theory of evolution. They kind of have similar words and they kind of apply to the same subject. One is philosophy and another is science, and molecular evolution by now became a true science. Then there is statistical analysis for natural languages and learning mechanisms, specifically how you learn languages and mathematics. I'm not concerned about how you learn, something trivial, which is lots of study, both mathematically and by psychologists, but this kind of subject you know anyway, but then how you learn languages and also how you learn mathematics. The answer must be mathematical. It's not just words. It must be some specific algorithms. You have to indicate at least direction how to build specific algorithms made on statistical analysis of the data. And for that, of course, you have to understand mathematically what is a natural language. And by the way, okay, we come to that in a second. Now this is a kind of preparation. And now there are two questions which go along. What is entropy, and is there non-Shannon kind of information? Because people speak about information in biology, right? This kind of flow of information in cell. People say there are flow of energy and flow of information, and this really guides biologists. But mathematically, we don't know what it is. And it's very different from entropy of Shannon. Of course, for that, you have to analyze more carefully what is entropy of Shannon. And so what is entropy of Boltzmann? And this we shall discuss at the beginning. And now we look in a few words of history. And it's strangely enough, unlike many other domains in science, it starts not with science, not with mathematics, but with gambling. And it can be traced as long. And actually, these kind of cubes were found in Persia that old, so 5,000 years. And people already understood, I think, more or less what we understand now. However, in modern time, this was kind of ascribed by Cardano. These people usually, some people speak about Pascal, but he was one of many, and I don't think he was. Say Galileo, there are some writing of Galileo which were published later on, which indicate he understood perfectly well everything was done by either by Pascal or written later by Huygens, but not probably the law of large numbers in full generality. But if he did already Cardano, he understood much more than you can believe, and actually saying many things you would never imagine. In particular, he was justifying psychology of gambling. He was a gambler, and he was an incredible character, and he was a great gambler, and he explained what's so good about gambling, psychologically, not only mathematically. But this is a minor point, and then there's another point which is more scientific. Oh. And which is not often realized was so crucial for probability, and so it's Brownian motion. It's again, I'm using history, and so can you guess who said and when was that said?
Democritus. Democritus.
No, but it's closer to the truth, yeah, than whatever we can say. However, you know, this was, as you know, sometimes ascribed associated with him as Brown, who certainly did not understand it. And amazingly enough, Tito Lucretius who said it, and who understood it, and he understood, in fact, many other things. And what is, of course, interesting about him, he was not, here's a picture, that he understood many other things, but he was not really a scientist. It was common knowledge at that time, yeah? However, how could it be? Because, see, people argued about Brown if who could see actually Brownian motion. He, of course, was not the first to observe it, and his contribution was kind of minuscule. Just name was easy to remember, yeah? Brownian motion only because the name is simple. He was a very good microscopist. He was a biologist, and he studied cell and made some discoveries about cell, but this was his hobby, and he observing, and well, everything was written about him is wrong. He was not doing what people say he was doing, and he has kind of the tangential relation to Brownian motion. But what's essential about Brownian motion, that this was the source of actual accepting atomic theory in the modern time, and because it allowed analyzing that was needed for measuring, for computing with sufficient degree of precision the Avogadro number. And who done that? You know who was the man responsible for that? And it was, you never heard of the name, of course, about these names, yeah, but this is ascribed to Einstein, and this is his most cited paper. It's not relativity. That was his major contribution to science, according to citations, right? Because it's cited everywhere, how you determine. And then there were experiments made here, I keep forgetting this, French great experimentalist, who was a few years later made experiments using this equation, Einstein-Smoluchowski equation for computing Avogadro number. But it's kind of tricky. Nowadays it's done quite differently, not like that. So, but again, interesting enough, mathematics was that done before Einstein 25 years later, and then usually mathematicians call it Wiener process, though it was 50 years after it was actually done by Thiele. The name of Batchelor also, you know, you probably know the history. It was forgotten, then came back, but he was not the first. Yeah, apparently it was Thiele. Now on the internet you can find many interesting things. This I just find on the web. Maybe there are all the sources, but this is all this I found. And then, of course, these words, by the way, how Tito Lucretius could do that? Apparently, some people doubt if Brown or people who, I forget his name, who looked before him 6 years ago, how could they had enough ability in their microscope to see it, yeah, because it's on the boundary of what you can see in a microscope, because you have to see particles of the size about 1 micron, and on them you see effect of when many atoms hit them simultaneously, and that's marginally can be seen in the microscope with 1,000 microscope. But how Tito Lucretius could come to this idea? Because he couldn't see that. But what could he see? He saw, of course, particle of dust in the sunlight, how they move. And it has nothing to do, of course, with Brownian motion. Yeah, it's just, you know, convection and turbulence in the air. But however, he made this, and that's very typical, by the way. This is exactly like Darwin, yeah? What he was saying was kind of right, but on the basis of sheer nonsense. And for that, he's considered a great scientist. Yeah, if you see, specifically, if he explains something, everything is wrong. However, well, it's like Lucretius. In principle, it's still right. Yeah. However, he is not. Lucretius doesn't give him this famous Darwin. So he understood evolution already as well as Darwin did. Yeah, on the basis, of course, of that. That's another interesting point. But we shall come because it has something to do with. Oh, what the hell is this? Right, that he articulated this, and one point which certainly opposite to what we can say from the other great thinkers, that it's not numbers which are kind of essential, because 20th century, then part of the mathematics was dominated by Grothendieck, and Grothendieck certainly wouldn't accept numbers above 2. Yeah? I think 2 was the greatest number he would ever accept as a number. So, but of course, the number is a great thing, and it was, okay? And then a big step in conceptualization of probability, you know who that? It was Buffon. Yeah. And again, historically it's amusing because Buffon, again, as far as evolution theory concerned, I think was understood much better, or at least he was handled as earlier than Darwin. But then he's kind of stupidly rejected, starting from Darwin himself. And because I was recently looking at the history of that, and it is completely distorted. In particular, a problem with Buffon, he was saying all the right thing, but then immediately saying, no, I don't believe it, it doesn't agree with the scripture. And they say, oh, no, he didn't believe into evolution, he didn't believe into that. He perfectly had a very clear idea, and not as detailed as Darwin, because some geology was not quite ready, and for him it was more conjectural. And because mathematician, he probably saw the flaws of naive kind of selection theory, which Darwin didn't. Darwin actually saw them, but he still believed it's true, and he was right, yeah. And then the point of application of probability in physics and much in mathematics depends on symmetry. It doesn't depend on kind of conception of chance, whatever. And that I will explain in particular examples later on. So that mathematically introducing probability is modifying the symmetries. You start like with permutation group, you have equal points, and then you linearize and a full linear group, or orthogonal group. And then mathematics become more interesting, and you can use it more efficiently. And one of the big discoveries in probability in the recent years was, you know, this is Shramlov evolution equation, one contains two crucial kind of ingredient of characteristic of probability. One is high symmetry, and secondly, that what you consider the random objects are not just random in unspecified sense. They're parameterized by independent variables. And in this particular case, they parameterized by Brownian processes, which are kind of, in a way, maximal independency possible for compatible with continuity. And so the Buffon, again, so he was throwing this needle, and actually, again, there is a folklore story. He was actually experimenting with that. He was throwing baguette on the floor somewhere and see how they will position it there. Yeah? And that was crucial point of the probability, because before that it was rather discrete. And there were computation, kind of kindergarten computation, done by great people like Galileo or Pascal, but they were kind of kindergarten in a way, because there was no continuity. It was just counting numbers. And here it was integral formula. It was hard measure. It's entered. And then this point of view was taken over in an abstract context by Kolmogorov, and he said, aha, that's the only probability which exists. So any probability can be modeled in the following way. So I want to give an overall scheme what probability is in order to just to move away from it. And so that's the logic of classical probability. You can say some measure space, universal measure space, I say square, interval is too small, you can't see much. Events modeled by measurable subsets, whatever measurable mean. Nowadays we know measurable is a questionable concept because it depends on axiomatic, right? So it is measurable, but anyway, the subsets, and its area is probability. However, if you look from, again, perspective of algebraic geometry, you see the faults of that, because it's exactly how André Weil was formalizing algebraic geometry. And we know it was dismissed in a decade, more, less than that, by Grothendieck approach. And the point is, both so in algebraic geometry it was a universal field. You introduce universal field absolutely ad hoc, having nothing to do with the object you deal with. And it's kind of convenient domain to do it. And again, my experience when I was learning it, I thought it looks so nice and natural. And when you do what Grothendieck does, it looks absurd. But it's exactly because Grothendieck was really seeing better than students and then another way. Yeah, it was really the right way, and with probability, what Kolmogorov done, in my view, is like this naive application of set theory. By the time it was done, you know, it was 70, 80 years ago, it was okay. Nowadays, it looks extremely naive. And you need change it, and indicate, I don't know how, it's easy to criticize, it's harder to make right thinking, right? You see faults, it doesn't mean you know how to correct them. So I indicate possibility of correction, but certainly they hardly will be of the level of Grothendieck approach. And then, of course, there is a quite different problem. So one just within mathematics, and just even in the context of statistical mechanics. If you look carefully, you don't honestly use probability the way it's described by measure theory by Kolmogorov. It just doesn't work. You always make some little turns here and there and just pretend you use it. And then you start making computation, and then how you make computation doesn't depend on your background up to a point. But from some moment on, it may depend. And then, there are other domains, and I mentioned them like languages, and then there is this statement by Chomsky. He had a very powerful kind of character, and he shaped, up to a large extent, modern view on languages. And mathematicians sometimes say that a language is just a measure on the set of words. And this, again, I think, super naive point of view, right? It just, in many respects, it's wrong. It's wrong mathematically because language don't make a set. Actually, Chomsky and this guy also say a very stupid thing. For example, they say there are infinitely, or you can make infinitely many sentences in a language, right? And that, again, completely absurd mixture, and this is essential point I will be discussing of this at some point. You mix model and you mix kind of the object, because the total amount of sentences we ever can make on for the time of the universe maybe 10 to the 20. It's much less, of course, 10 to 15 maybe, or 10 to 16. We don't know time. The universe is very small. Time is very short. Infinity is not infinity. It's a very small number, and it's essential for these structures to understand them. This kind of structures, this also applies to what I was mentioning before, biology, like molecular evolution. The scale is essential. You have to, numbers are essential, but they're a finite number, and all your means must be adapted to them. In physics, sometimes you can pretend numbers are infinite, and for good reason, because the group symmetries are very high, not because the numbers are really large. Because the point why you can say is meaningless. So there are many ways to justify it, and this is one is that probability is very small. When you have a certain sentence, its probability will be 10 to the minus 20 or minus 15. And it's a very small number. We have a sentence of the length of a dozen of words. Probability of this actually appearing will be 10 minus 12. And this is a small number. But in physics, you have a much smaller number. In the statistical mechanical particles, you have 10 to the 26 particles. And each of them may be in, say, in 2 states. So I have 2 to the power 10 to the 26. This 1 divided by this number, right? So maybe I will write it down. It's a very small number. We should say how this probability is 1 divided by 2, at least 2, yeah, to the power 10 to the power 26. And this probability of a particular state or a system of particles in this room, it will be probably maybe 29, yeah. So the state of this room, particular state, has this probability. Of course, it's nonsense, yeah. But however, you can use statistical mechanics. And interesting point is, though these numbers makes no sense, right? You have this state, I don't know what it is this state, and the probability makes no sense, but the quality of these probabilities still makes sense. And that's point in mathematics. Objects, numbers, and I meaningless, it's okay. The relation must be correct. You have to know how to manipulate with them, and then you go on and on and on. But there's a starting point. There is symmetry in this, in between the particles, because all particles are essentially identical. Therefore, you can speak about this identity without knowing what the subjects are. And this will be a kind of essential part in many applications of probability, what I will be discussing at the end of my lectures. Yeah. So these are two new ingredients which come to probability from 20th century, which were not available to Kolmogorov, and one of them category theoretic language, and secondly non-standard analysis. And actually, both of them very close to what Boltzmann was saying and thinking. If you read Boltzmann and translate it to modern language, this is what you see. People were translating him, of course, in the 19th century, at the beginning of the 20th century, to the language available to them, and sometimes saying, well, he was saying not quite right, you can't, that mathematically doesn't fit to anything, because mathematics was not ready. That kind of, now mathematics is better adapted, and there may be something else, in particular, the concept of the entropy, the definition of Boltzmann, which he had in mind, I guess, of entropy, and what you can find in elementary physics textbooks, entropy is log of the number of states. And just decipher that. It's not writing formula, right? So when you write the formula, mathematicians make kind of double mistake. So you write the entropy is minus some pi log pi. And kind of very proud giving the definition. In my view, this is a psychological phenomenon where you, in the audience, people who never heard of the entropy. And you just say, that's the formula. Why? Because I'm smart, I know the formula. No, it's a bullshit. It's not a definition of entropy. It was computational formula invented by Boltzmann. And it's an extremely useful formula, but it's not definition. Definition is, it's the number, log of the number of states. Right? And how to go from this to that, you cannot do it in the, unless, from my understanding, unless you pass to more sophisticated language. And for this, and I explain it today, you have to take categorical point of view. And in physics, it's exactly kind of categorical point of view is everywhere present in physical reasoning, in naive physical reasoning. But it was translated automatically to archaic mathematical language. It became kind of fossilized. It became kind of stereotype. The formula is a great formula, but it's actually, you know who wrote this formula first? It was not Boltzmann. It was Max Planck. You know, there was a nice exchange between Max Planck and Boltzmann. Max Planck wrote this formula, and Boltzmann suggested discreteness of the energy. Quantization of energy was the idea of Boltzmann. Yeah, it's interesting because Boltzmann was obsessed with the idea of quantizing the world, of having discrete atoms, and also he believed the energy was discrete. But his speech, this is actually you can find this even on Wikipedia. It's the kind of standard knowledge nowadays. Where you have access to knowledge which you didn't have before. And so, alternatives, and this we shall discuss, are the following. So one is Grothendieck type of describing entropy, and this I can, part of mathematics I understand well and will explain today. Secondly, along that you define probability spaces also in the spirit of Grothendieck. Because you see, the problem is that every time in traditional application of probability to turbulence, whatever you say, there is somewhere over you, this is some probability space, and you do on this probability space, which is rather nonsensical. Exactly as Weil was doing his algebraic geometry. There is this field, and you take points in this universal field. However, nowadays, the concept of functor of points, it's a function. You take domain, and depending on domain, you have your points. And the same in probability. Depending on domain, you have your point. And this means you consider a functor from some simple category to category of sets. And once you do that, measure theory, in my view, become extremely transparent. There is nothing to prove. You just always Lebesgue integral become tautology. Because categorical language immediately tells you what you have to check. And checking is usually trivial. But it gives you structure extremely nice and simple, and I will explain that. And then another point is, which I understand less, is kind of large deviation. What is the right setting for large deviation? How it goes via non-standard analysis and geometry. Something I can explain, something I don't quite understand, both in classical and quantum of von Neumann entropy. Because we shall see understanding this formula. Well, there are two ways to think, two ways to come at this formula. And one of them immediately brings in von Neumann entropy. And this suggests different, again, linearization. And again, from my point of view, that's because it solves some mathematical questions, though it looks absurd physically. When you replace measures by something linear, like some homology, or rather cohomology, And another subject, when you apply that, try to apply classical kind of probability to something unruly, such as languages, learning, or even molecular biology, you see that just you cannot assign numbers as probability. It's something else. They're kind of numbers, but not quite numbers. And that's kind of the last so what I did now is cut and paste, very easy. I make the spacing from some of my articles, which you can find on my website, and that's their names, where there are more details. And now I want to go to entropy. So before making, so again, I like quotation, yeah, because they give you some perspective. No, because whenever you want to say something, you check and see it already has been said. And of course, as you know, one of the points of modern science is that you cannot understand nature by pure thought. And Einstein was exactly arguing with this point, that reality can be grasped by pure thought, and up to a point he was right, but then he happened to be wrong. With quantum mechanics, it didn't work. And then, again, in quantum mechanics, it's unclear what reality is. And that's, again, a very interesting point. And so how to make, you can make mathematical model of reality, but what the hell is reality? And then the last great man who said something was Alexander Grothendieck, said, in order to understand reality, you have to understand what zero is, yeah, so to speak. And that's, let's try to go from zero level and try to understand entropy. So first, this is a physical language. We want to translate to the Grothendieck kind of language what is entropy, right? And so just first say what physicists say. So they say we have a system, right? Whatever it is, a mathematician will say, oh, it is a set, all states, da. Why set? Set is just language invented by Cantor for a certain purpose. It's very flexible language, but it's still not the only language. It doesn't mean there is a real states, yeah? When I was saying about that, each state having this probability, of course, they are not real states. Yeah? These numbers, even physical real numbers, they don't have physical meaning. It's just up to a point. You play with them, but they're a real number, but they're not physical reality. And actually, there is no such thing, of course, as physical reality, right? And so that's how you can. This is a kind of physical preparation of that. So you don't have this physical state. What physicists do, they make experiments. They have this, so like I prefer to speak about crystal, but maybe a continuous system. And they make some measurements. And the measurement described a protocol of how a measurement is made. And this, by the way, typical for all experiments, which usually disappears when mathematicians look at that. It's a protocol which is being used. Mathematicians think maybe to measure a protocol, they don't know the result, because mathematically, description of the result of experiments following a protocol described in the language of two categories. And of course, people who do applied mathematics don't like two categories, right? But these physicists automatically use this language. That's another point, that categorical language is the most, or even two-categorical language, by far more primitive and simple than usual language for mathematicians. The traditional language developed by calculus, whatever, it's super sophisticated thing. Yeah? For example, if you want to study basic property of entropy, for example, concavity or convexity of this function, then it depends on of knowing what is derivative of log. But if you look categorically, the only mean, if you use the right definition, it's just the only thing we have to say that it is kind of natural definition, functorial, and then all properties, including basic property of logarithm, would follow. That's kind of amazing, yeah. You don't have to make computations. And this is again in the spirit of Grothendieck. You don't make computation. Emphasis of what Maxwell was saying, you make computation, and physicists now in quantum mechanics say you make computation, you don't think in philosophical terms. But I think you have to think in mathematical terms. And this is what's happening actually in development of physics. Yeah? People study physics, now think as mathematicians. But on a much higher level than the one which I am considering. And so there are this machine, some equipment, you make some measurement, and so what you observe either something, kind of in a way, something happens or doesn't happen. Something blinking on your screen or not blinking on, and just you count how many things happening, and from that you want to define entropy of some incomprehensible thing like a crystal, which has no states whatsoever in a sense of kind of from physical point of view, right? So again, so one thing which we want to avoid saying is that physical system with so many atoms may have some space of states having so many states even in the discrete sense, whether they're kind of black or white. Yeah? And there is a lot of kind of confusion with that, even just one with typical discussion. If you know, that's, in this context now, quantum, you know, this paradox of Schrödinger cat. If Schrödinger cat being kind of secretly poisoned, you don't know that if he is in the state of being dead or in the state of being alive. And this is exactly kind of also confused because there is no such thing as state. State is a mathematical word to describing something, and the description is not adequate even in very simple situations, not to speak about quantum mechanics, of course. However, how to speak about that? And now let me now explain that, and this will be simple mathematics. Maybe I go one step ahead of myself. So 1 and 2. So this sum. So this one is functorial, and which I'm going to describe functorial description of that. And the sum is analytic, but analytic in a different spirit, because this I explained it, but of course this part I don't understand well. I don't know it well. Not well. I don't know it at all. It's the phenomenon that much of physics on a high sophisticated level depends on taking certain particular integrals, right? It's kind of, you integrate something rather complicated algebraic expression, and they come out of that. And by now there is very developed theory of that integrals, and that's an instance of that. So this function is some kind of remarkable integral. And from certain point of view, so this pi numerically are numbers such that their sum equals 1 and they are positive. Therefore, it's a function on a high-dimensional simplex, right? So if you have this I belongs to index set I, so I have two Euclidean states r to the power I. This again, by the way, I use set-theoretic language as it should. And again, I insist on that, because if you don't do it, you immediately run into a mess. I don't know, for example, what this means when n is a number. This notation is certainly incorrect. And the people just much do that. What the hell it means? What is n? N is not a number. Here, n is short. Usually it means this set. But there is typically no numeration by numbers. You traditionally, you put these numbers everywhere where there is no numbers. Set theoretically, you can power one set and the power of another set. And that's a perfect definition. Why I insist on that? Because this is preserved symmetry, it's functorial, and this is not. It's completely different category. Here is category of sets, of i's. Here, at best you can say it's category of ordered set. It's okay, but it's a wrong category. It's exactly which wrong in physics, yeah? You have so many particles, they are not enumerated. You have this particle, so many particles. It's not even set, yeah, truly. But even if you accept it set, it's not, you cannot enumerate it, because the number of enumeration is this number, this factorial. It's even bigger than this number. So you arbitrarily take something from this number. So you introduce a structure by overriding everything you do. And then it produces tremendous mass in description, yeah. So the point of categorical language is really much simpler, much shorter. And I shall explain later on what the advantage of that say in the case of that. So, but what's analytic point about integrals? They're called period integrals sometimes. So I'm saying that this function is the simplest possible function in the n simplex. In what sense is it simplest? Of course, it's having maximal possible symmetry. Of course, the maximal possible symmetry will be kind of zero function or constant function. So this we reject. Now, analytically, So given a function on a simplex, you want to characterize this from the point of view analytically by its derivatives. But certainly gradient is a gradient, you cannot say much about it. What you can see first, one kind of some function shows its features is when you take it Hessian. So it's a table. I wanted to say matrix, yeah? It's another, by the way, quite embarrassing thing in mathematics. What is matrix? What is a matrix? Mathematician, you're a mathematician. To give mathematical definition of a matrix. Can anybody give me a definition of matrix? Huh? No.
It's a function.
Huh?
It's a function.
Function where?
From the set of n times n elements into R.
It's a function, but n, no, so it's a function on set. N is irrelevant here, right? There is no n here. This is a function, yeah, on this set. So it's, of course, it's not a matrix, and the Hessian is not a matrix. Hessian is a quadratic form. Because it doesn't depend on n. It just says that for any pair of vectors, you take this derivative and you have a result, and this will be quadratic. It happens to be written, but as for matrices, of course, yeah, what you say is okay, but it's not quite true, because very often matrices like that, with unspecified entries. When you don't say what's in this entries, you say matrix with some entries, you don't know what entries are. They are not functional in a particular domain. So that's a tricky point. So in a specific context, you can say what you mean by matrix. But generally, matrix, you confuse in mathematics intrinsically with the way you write it on the blackboard. And this everywhere, by the way, in mathematics, it looks a joke what I'm saying, but you cannot, for example, explain that these two implies. Do you know that this is not that the question is unprovable? It makes no sense in mathematics unless you write it on the blackboard, because you know by blackboard in which order they are written. If you don't have it, if you have no a priori order in your head, coming either from blackboard or the temporal order, you cannot make sense of this sentence. And that's, as we shall see maybe in the end of my lecture, is essential of trying to model learning theory, how we learn things. And as you know, small children don't just have no order in their head, right? They have great difficulty distinguishing it. And all mathematicians make mistakes reversing inequalities, you know? You know there is inequality in the right sense, but which sense? And it's not accidental, because this is an artifact of mathematical notations. And it's not in our head and not internally in the mathematical structures. So that's another point, yeah? And again, it may look a joke, but when you come to the end of my lecture, I see that without understanding that, you cannot understand the learning mechanisms. And as you know, for 60 years, more or less, there was tremendous failure with so-called artificial intelligence. We're making claim after claim. There's absolutely no progress. There is a lot of progress, of course, in hardware, in a sophisticated software, but nothing kind of close to what was expected to be done. Yeah? You cannot make any simple intelligent program. Right? They're all expert programs. You exactly say what to do. And this is one of the reasons, because we have a very wrong idea about how we think. And the first fundamental mistake, we think that we think. Yeah. Okay, now, so what's about the Hessian? So Hessian is a quadratic form. And then, what will be the simplest quadratic form? And think about quadratic form as a matrix, as a metric. It's a Riemannian metric. What is the simplest Riemannian metric you can imagine compatible with the simplex? One of them, of course, will be just the one you see. But another one, if you think about the simplex as a part of a sphere, so a spherical simplex. And then you have a symmetric of constant curvature. So 0 you cannot have, right? It will be constant function. But this is the next potentially simpler thing. The fact you can represent metric of that kind as a Hessian of some function a priori seems absolutely unlikely, right? Because, I mean, this is the number of possibilities for function, the number of quadratic forms. Quadratic forms depends on n plus 1, n minus 1, I keep forgetting, but square number of variables for n variable, right? And here we have only one function. So very unlikely you can hit some target like that. However, entropy does that. So entropy, this is miracle, right? And that, by the way, another point, of course, about mathematics. When you apply mathematics in this context, it always depends on miracles, right? It's not illogical science, unlike everything else. It's against any common sense. There shouldn't be such function, right? If you ask a priori, is there a function beside problem? Of course it shouldn't be there. However, it's there, and this entropy. And intrinsic symmetry of entropy is orthogonal group, or rather Lie algebra of infinitesimal motion of the sphere. And this is what automatically transplanted to quantum world. So this formula, written by Planck, is contained inside the germ of quantum mechanics, which is rather amazing. I don't understand why. Of course, there are some. Nowadays, there is geometric quantization, time, and physicists say they understand it, but we shall see there are lots of questions mathematically, we don't have answers to. So there are two aspects of entropy, and now I make a little break, and so on the next lecture I explain how you define entropy in the style of Grothendieck, kind of categorical language, without ever mentioning any numbers, yeah? Almost without mentioning any numbers. But on the other hand, it will be kind of understandable, in my view, in principle, to a child. Unlike, you don't have to differentiate, you don't have to know what logarithm are, just nothing. You just have to know what stones are, so to speak, what water is, right? Okay, so let's make 10 minutes break. Okay, so I want to take now this category theoretic language. And I want to understand this sum. And so it's about these numbers. And these numbers are weights of something. They are masses or measures. And so I imagine, this is of course not necessary for definition, but the picture, they are not numbers, they are drops of water. And total amount of water is fixed and called 1. It's just called 1. It's just the same amount everywhere. And then what you can do with this, everywhere you can do that, you can bring these drops together and have one bigger drop, and the others may not change. Or you can simultaneously bring two of them together, become slightly bigger, right? And that looks rather innocuous. However, mathematically what we have this pi, collection of these atoms, or drops, and which have weights denoted like that. And these are numbers. But fundamental objects are these drops of water, not numbers, right? However, you can present them by numbers. And the point I'm making is because in some other cases they are not numbers. They happen to be numbers here, okay? And you have morphism in this category, and what physicists call reductions. By the way, maybe, and this is a good word. But maybe before I said it, you may have questions concerning my first lecture. Huh? I don't think there were questions yet, it was just general talk. Now you may have questions. And so you have the spaces, P. So these are finite probability spaces. And this what they are, but again, categorically, up to some moment, you don't care what they are. What you know that there are errors between these objects. So there are objects, they are finite probability spaces. Actually, they don't have to be finite. They may be countable, but that's too complicated. And there are these arrows between them. An arrow exactly this process. So each of them given by set of these PIs. And so what you do, some of them can merge together, and the weight you assign when they merge, there's sum. Right? So there is object with weights, and then there is arrows. So numbers additivity is already encoded here. So the point of category theory, you already is in the rule of this. In this arrow, you have this arithmetic operation expressed in the language of these arrows. And this, of course, category was good about them. That's universal language. And universality is kind of the source of all science and mathematics included. Yeah. including probability theory. So now, of course, they are very special, kind of special category. One can say, aha, it just means that this space P is kind of greater than Q, right? That Q is a reduction of P. And instead of saying there is morphism, and morphism has name, you can write like that. So what is advantage of categories? There are many of them, but one of them kind of evident. And partly has something to do with this problem, how you distinguish this sign from this sign, yeah? In your mind, yeah? It's indistinguishable, yeah? So, there is such a conception as relative entropy, yeah? And relative entropy applied to the pair of spaces, satisfying this relation. So say, well, there is this order, if there is this error. And then you have to write something like that. Entropy of P, comma, Q. Some people pay H, whatever letter, I write entropy, yeah? Because you need one letter of only when you start doing complicated computations, but we shall never make any computation. Everything comes by itself. So I can have this notation which is easy to remember. And so you have here three symbols, P, comma, and Q. And besides, you never know how you can tell this from this. Actually, when this relative entropy, I mean, myself, I always lost. Who is who, right? Unless you write this arrow. However, if you use this notation, you just say entropy of F. And you have only one symbol. Moreover, you know categorically when you have something defined on objects, how automatically it passes to morphisms. And this typical category, you don't have to think. You don't have to define this relative category. It comes to you by the language of category theory. So once you have idea of absolute entropy, automatically you have relative entropy with all its properties. Sometimes you have to prove it. That's another thing about categories. Not that they give you the proofs, but they tell you what to prove. And then you may or may not prove it. And then notationally, so you reduce three symbols to one. And that's not so bad. So your paper may become 3 times shorter because it carries lots of junk, usual notation, and this happens for most mathematical exposition for some reason hard to explain. Most of what we write in the paper is junk, completely immaterial. It's just brought there arbitrarily because we don't know how to say it well. Right? We cannot express our ideas well. The best we have category theoretic language, which is not perfect, but still certainly much better than set theory, infinitely better than analytic language, yeah, of course, yeah. Which is just truly horrible. And it's not really only understandable in some very kind of very specific, unclear what kind of sense, you know. That's again the issue we shall come later on. What is learning and what is communication of mathematics? How it happens, yeah. Because and it has little to do with logic, of course, but something to do with probability properly understood. Okay, so after this little kind of propaganda, so you have this category, call this P. I don't know how to call it. This is a category of where objects are probability space and morphisms are reduction. What it corresponds physically, by the way. Yeah? Immediately, it's very nice to have these various pictures in mind. One is when you have the drops of water and bring them together. Another, of course, more with reduction, has the following kind of point of view. So you have this finite probability space, some physical machine. Yeah, it's a physical system. I don't know what system is, but it's a system exactly to avoid saying it's a set or whatever. It's something you observe, and you see some flashes of light coming there, and you count them, and inside there are finitely many windows, so a thing divided into windows. This windows indexed by some set I, and there are frequencies of something happening there. And you normalize them, and you have this bunch of numbers. But then you can put some filter and just attach to this, not filter, but some other thing, which will depend only on what happens here. And then you have another number of windows, maybe bigger, maybe smaller, I don't know. Actually, the one which are bigger, they will not blink at all. But you have kind of smaller thing, and the blinking here determined by those. And that's how we think about this reduction. And later on we shall see how with that you can define infinite measure systems, and how you can define basic concept of probability theory and actually automatically prove them sometimes. Yeah? Once you find them, usually proof is very easy. Okay, so that's the category. And now I want to say what is entropy. Now, a category has nothing, a priori nothing to do with numbers. It's just abstract thing. It's just, again, it's not so obvious what category is and what definitions tell you. Because you can say, it's kind of a graph. So there are points, and there are these arrows. And so it's some particular graph with arrows. But then there is, of course, extra point that you have a rule of composition of arrows. There are certain distinguished triangles. And these distinguished triangles say this arrow composition of these arrows. And also there are distinguished arrows, distinguished loops, which are called identity morphisms. And again, it may look stupid. Why not just to say anything? But it's crucial for having right structures. If you describe something that doesn't quite fit in this setting, something you do is wrong. Of course, sometimes category theory is insufficient, but mostly you're still doing something wrong. It's amazingly adequate language in mathematics, and unclear why. It works so well. So, but the point is, it's not a graph. It's not like that. It's something you do this. What you do with this is very different from what you do with graphs. Sometimes you do something similar to what you do with graphs. It's somewhat different. And it's hard to say exactly what it is. So, from that point of view, you cannot give definition of categories. And that's another general principle. If you try to define some general concept in mathematics, you usually say something stupid, because they're undefinable, it seems to me. I never saw any meaningful definition of a function, of category, even of a set. Yeah, right. But there are kind of limited definition. But what is the language or whatever? You cannot define it, but you can live without it. Yeah, and that's again the interesting point. I just several times was bringing it when you say about function, that function of a real variable, then for each x you have y, yeah, and these are real numbers. And this is it's nonsensical. It's kind of the only function of this definition to bully the audience. I never heard of that, because the audience, everybody knows, everybody understands that these are two functions. Yeah, here is 0, here is 1. But you say, no, it's one function. You can say it, but it's stupid. Yeah? It's two different functions. And so we don't know what function is. And this kind of, maybe if you give a big audience and you admit you don't know it, well, so a professor is supposed to know it. But I think it must be realized that science and mathematics in particular, it's not so much of how much you know, but how much you don't know, right? Scientist is different from a person. He doesn't know anything, understand nothing. And the common people understand so well. That's the point. Actually, Feynman made this point, yeah? You always live in the state of full non-understanding of anything you meet, yeah, and that's okay. This is how you can make next step. Otherwise, you're blocked. If you understand it, you don't move. Right? It's a non-equilibrium state. Anyway, have this category, and now we want to define entropy. And it's supposed to be a number, but should it be a number? If you're in category, there are why numbers, and so there is the following general construction applicable to any kind of category. You do Grothendieck and call Grothendieck group, or rather Grothendieck semigroup. And the simplest thing you can do, it's kind of describing a group where these morphisms F serve as generators, but I take classes of them, and the basic relation is that if composition of this equals H, then it implies that F plus G equal H. So you consider groups generated by symbols corresponding to arrows, and you say there is this single relation. And now I say some words, and when I decipher them, first I explain how they fit physics and how they fit mathematics, and so what happens from that. And now the point is that, because what I will say now will be not literally true, and I explain kind of the subtleties of that, but it's true in spirit. I'm saying is that this, if you apply, take Grothendieck semigroup, say, the Grothendieck semigroup of our category of finite measure spaces, then this is canonically isomorphic. And this might be corrected, yeah, maybe to make more precise, to the multiplicative semigroup of positive numbers greater or equal than 1. And this is a theorem. Right? And then why numbers enter. When you take log of this number, you have entropy. And this log of this, so it applies to already to morphs, not necessarily to objects. When you have an object, you have this distinguished element when all drops come together, this particular arrow. So when you apply it to object, you apply it to this arrow. So it's immediately defined for arrows, not only for objects. So immediately defined relative entropy is much easier than absolute in this context. Yeah. And then there is a theorem saying that this semigroup, it's abelian semigroup, yeah, it's canonically isomorphic to the group of real numbers greater than 1, and you take log, and log is justified by the second property of this, because formulas become kind of miraculously well good. If you don't understand why, it must be like that, yeah. The deep reason, mathematical reason for me is completely kind of unclear. But that's the theorem. And you know who proved the theorem and when? Who proved the theorem? Yeah? I never heard of this guy. And it was Jacob Bernoulli. And this is called the law of large numbers. So if you properly interpret the law of large numbers, you arrive at this conclusion, except one point. Except what point? It must be topological Grothendieck group. Now where geometry or analysis enters. The categories you work with are topological categories. Besides arrows, there is a concept of two spaces or two morphisms being close. And these need explanation. So you have to use the right topology. Okay? You have to use the right topology. And the way you use kind of, I cannot tell, either the weakest or the strongest topology where it makes sense. The one which is the hardest to get. I never know whether the weakest or hardest. Yeah, this is exactly this problem with the signs. Yeah, you just never know. And and then from that many kind of things follow that. So what is behind it? So what is behind it? And so to get some feeling of topology, I have to consider an example which for me is kind of the source of an understanding of that. So to get some picture, some ideas of this category and of that, let me look at one particular class of examples. When you have spaces P of the type Pi equals to Pj, well, all enters are equal. And so what happens to our category? And so what is kind of the point of the theorem? Now, so what will be arrows here? So this will be just a bunch of numbers. And say you have now I use, say, hate indices, yeah? Because notation already ready, and I don't want to invent new. You have n numbers, and then you go to another one, to a q, when you have m numbers, all equal. So what will be such an arrow? It means that number n will be decomposed as m times another integer. So if you restrict this category to atoms of equal weight, what you have just the composition, multiplicative decomposition of numbers, of integers. So this category, on one hand, you see I was adding numbers. on the other hand, here you see there is multiplication built in. So the whole arithmetic is in this category, which is kind of rather powerful. It says that you don't lose what you had. Yeah, it's always there. And so, and then this kind of, and then, if you look at this, what this kind of semigroup will be here, it will be just all multiplicative rational numbers greater than 1. Because here's the integers, and then you normalize them by the common denominator, and then what you have is just all rational numbers. But if you do it here, if you do it for in general, you have kind of huge, kind of uncountable, some horrible space if you don't put topology in, right? Because it becomes a kind of, if you put here different irrational numbers which are linearly independent, all in Grothendieck groups they will be different. Yeah. Right? They will no relation between them. They have to somehow bring them to glue things together also by topology. And now I want to bring a geometric example which kind of clarifies what happens, because this kind of so far is abstract. Maybe just first of all, maybe before doing that, I explain what the law of large numbers has to do. Which was proven by Jacob Bernoulli in 170 something, yeah, and he actually tried to prove it for about 20 years, yeah, before he proved it. And I don't know actually what was his reasoning, yeah. It has already been conjectured by Cardano, who conjectured the law of large numbers. I don't know how Bernoulli proven it. I think today's standard proof using Pythagorean theorem. Of course, you know it follows from Pythagorean theorem, like many other things. So one of the great, so Pythagorean theorem, kind of one of the greatest theorem, and law of large numbers also not so bad, a direct corollary of Pythagorean theorem, and of course, you know why it's Pythagorean theorem, no? Okay, maybe I'll prove it. This Pythagorean theorem, of course, follows from that, but plus modern notations, of course. And so how you get it? So what is here? And then you also will understand what is topology involved. So if you live in this category of finite measure spaces, we observe there is the following operation. Two spaces you can multiply. You can take product of two spaces. And this is very simple. If this was built out of pi's and this out of qj, this will be built of pi times qj. And because the positive number, total sum 1, is kind of perfect product. And here kind of you can think about this, of course, as a matrices. Yeah? You have pi's here, qi there, and you take this product here and here. And then, once you can do that, you can write, which is kind of wrong, p to the power n. Meaning p multiplied by p multiplied by p n times. It's wrong because it must be set, and I put number. But very often only cardinality of set matters. Yeah? So in truth, you write here number rather than cardinality of this number. And again, without analyzing it deeper, you see you can't write the number, yeah, because, and it is you need this set because transformation, operation with sets implies certain operation over these powers. And I arrived at this kind of way of thinking rather recently when I was solving very specific questions when you're completely lost if you put the number. But I write the number, yeah, nevertheless. So meaning you multiply it by itself many times. You see what's wrong with that? Because I use notation on the blackboard. I write on the blackboard. If I have no write, I cannot write in the sequence. And that's what's wrong with that. Yeah. We want to have our mathematical description of mathematics free of a blackboard. And it's impossible. Yeah. No, not joke about it. It's impossible. Literally, it's impossible. We make some convention all the time. And you say, how I can verify mathematics on computers? But this depends, of course, kind of rigid structure of computers. Yeah. And sometimes may fail, and it's a kind of great miracle by mathematics still there.
Excuse me.
You don't need induction in this case?
Huh?
You don't need induction in this case?
I don't know what induction is. For me, all this logic, I don't know what induction is. For me, it's just empty words. I'm sorry. For me, induction is empty word. It's empty word, I mean induction. Because again, it depends how you write things on the blackboard. It's a language. Language depends how you write it down. I don't know what it is. We come back to languages. Yeah? I'm saying all traditional descriptions of mathematics, in my view, are greatly faulty. And that's the reason why there is no model of mathematics in computer, why there is no model of understanding languages, because we have absolutely wrong perception, traditionally built in the development of numerical mathematics and logic distorted our perception of ourselves and of mathematics and of languages. It's fully distorted. Like the same as speaking about sun going around the earth and making all this language describing it. It's just wrong. The sun doesn't go around the world. How it's kind of, you see it, you can describe it, you can do lots of this, just wrong. It's the wrong language, wrong description. And it's easy to say it's wrong. It's hard to say what's right. Right? You can philosophically say there is no reason to believe who turns around whom. We around the sun around us, unless you see other planets. When you have many planets, you say, aha, it's more likely we rotate around the sun. But unfortunately here we don't have much planets to guide us. But of course, incorrectness or not, or rather inadequacy of the standard description or prescription by mathematics, I think is rather apparent. And that's, so really with no induction what I'm saying. Because again, I don't know what induction is. You see, induction in mathematical logic is a kind of again, it's a greatly questionable thing, yeah? Like all this mathematical logic, you know, it's an interesting thing, yeah? You may think mathematical logic is very kind of thorough, very careful discipline where you never make mistakes. And in mathematical texts, great mathematicians never made mistakes, any serious ones. However, if you look at one of the founders of mathematical logic, Frege, for example, when he wrote his main book and the pub sent it to Russell, Russell immediately said, well, sheer nonsense. He's actually self-contradictory. And Russell wrote his text. And then Gödel was reading Russell and saying every line was mistake. Mistake or mistake or mistake. And I think what Gödel says also, it's wrong or wrong in a different way. Logic is absolutely unrigorous science. It's just absolutely just pure fantasy, mathematical logic. Of course, as mathematical theory, like model theory, set theory, it's okay. They're mathematical theory, within mathematics we accept them. But when logic says, I'm foundational mathematics, I'm logical, I'm correct, it's nonsense. But history of that shows it just always was wrong, right? Because it's just, it's not, there is no logic. It's illusion, yeah. In mathematics, it's something else, what I'm saying. There is something else, which is, of course, naively use logic, but as a great thing, you shouldn't use it. As set theory. As naive set theory, it's a beautiful language. When you go next levels, within itself, it's a good science. As a language, it loses its ground and is taken over by categories, which for some reason better. But anyway, what you have this product. And so now, if you have originally, say, to the power, so it's p to the power n, and say, my notation a little bit maybe confusing, p to the power n, and say originally this space was considering pi, and I was running 1 to say k, and then it becomes big space which has k to the n elements, is a huge space, and each probability of each event become absolutely small. On the other hand, it's exactly with what you have to deal in physics, where you observe events after events. You have this blinking light and blinks hundreds of times. So the probability of any configuration of blinking becomes something like 10 to the minus 100. They're incredibly small numbers, so you cannot explicitly make computations. For that reason, you need formula. And for that reason, kind of, without thinking, of course, Boltzmann had his formula. Physicists immediately invent formulas which are good for counting, for making definite results. And here in mathematics, we don't have to do it too prematurely. But, so what about this space? The point is, so there are this, as I mentioned before, there are very special states where all entities are equal, and they're kind of represented just by numbers, right? And their category correspond to multiplication table. So just multiplication table. And by the law of large numbers, this space p to the n in some correct sense converges to this, call them homogeneous space. It's asymptotically homogeneous. So when n is large, all entities become approximately equal. And this is exactly the law of large numbers. And if you decipher approximately, this will be the right topology where the definition which I gave become correct. In what sense approximately? Right? And you have to just remember what the law of large numbers tells you. In a second, I will explain this to you. And the moment you have it, this definition has the following power, that it tells you not only that this abstract statement, really this isomorphism, but it says that if you consider inside of this big category, this very small category, where all objects just atoms of equal weight and morphism between them just product of numbers, that this category dense inside. Therefore, any property which continues with respect to the topology I want to describe, and most of them are obviously continuous, if it's true for constant, for this kind of simple set, so this becomes just maps between sets. So they kind of all these weights disappear. And if something is true there, it's also true for general category. So many theorems become immediately apparent because of this density property. It's not only, so it's slightly more than that. Bernoulli theorem, if you look at the logic of that, tells you not only that space is being approximated, but if you have put here this morphism become approximated by just multiplication of numbers. And so this I want to explain in some example, how you can derive from that rather non-trivial properties of geometric objects. And this for me was somewhat surprising. I just realized the power of this entropy. Before, it's just a formula. See, I remember just knowing this formula, you never could swallow it. Yeah? It's just a formula. From geometry formula, it's just formula. So completely meaningless, you know. And then, interesting enough, by the way, this is a problem of modern, of course, computers. I needed, at some moment, some particular inequality about entropy. It's kind of trivially following from other ones, and I couldn't find it in the literature. I took all textbooks on entropy, and none of them was doing that, because all were repeating only what those was written in one of the first, I think, books or articles by Rocklin. And they were copying and pasting, copying and pasting, copying and pasting. Nobody ever, of the authors, tried to think what entropy was. They believed this right definition, just make copies. Yeah? And this happens, by the way, very often in science. You make copies. This way I'm saying history is useful, because you can realize, what we have is just mistaken perception. Now, so what's the example I want to consider? And this is close to my heart. Geometry is called isoperimetric inequality. So I'm saying that isoperimetric inequality follows from functoriality of the entropy. This from functorial definition. Just from the law of large numbers, essentially. So what is isoperimetric inequality? Say in 3 space. So in 3 space it says we have a domain and say omega, then volume of omega is greater or equal to area of its boundary, and you have to put the right exponent. Here you have to take, say, I think in this form, up to a constant. Universal constant depending on dimension, here dimension 3 is up constant. But for the moment I'm not very much concerned with the constant, though I just realized there is a problem with correct constant. It's sometimes very important to have a right constant. So this inequality, I'm just saying it, if you kind of apply this logic of this being almost constant, then it would, this statement which I said, that then it would imply this isoperimetric inequality. Which is kind of amazing, because it looks geometric inequality, you think you have to do something. But amazingly enough, you need to do very little geometry, not geometry inside. The law of large numbers takes care of geometry, which I think is quite amazing. So this is kind of non-trivial inequality. Yes, it's even already in dimension 3. All proofs require some idea, right? Because the trouble is in dimension 2, of course, they're all obvious. You have a short curve, you just integrate this area anyway, and so, of course, area less than square of the length, right? Because you integrate twice. Of course, sharp inequality requires more effort. But in high dimension, what may happen, you may have these domains, These very long, narrow fingers, which carry inside very little area, and who knows, they may carry lots of volume. This doesn't happen, but this you have to prove, right? So there is something to prove. This concerns what I'm speaking, non-sharp inequality. And this is what is relevant for most of analysis, so-called Sobolev inequality. All the Sobolev inequality is a trivial corollary of this inequality. By the way, there is one inequality which doesn't follow immediately from them. It's called log Sobolev inequality. Interestingly enough, that we shall prove with entropy will be this log Sobolev. It will be even stronger, up to a constant. The constant is another issue. By the way, nowadays there is no kind of good proof, good meaning just by formulas, of the isoperimetric inequality or sharp inequality. Amazingly enough, such proof exists in dimension 2. It exists in dimension 4, and that's it. There is a formula from which is apparent this inequality with a sharp constant is apparent in dimension 2 and 4, not even in dimension 3, not to speak about other dimensions. And it's hard, it's hard to correctly formulate that such is impossible for high dimensions because there is some. What do you mean by formulas? And the formulas are very simple in the case of 2 and 4. But if not sharp inequality, the proof which I give will be not by formulas, but will follow from this functoriality. And so let's prove it. First, the point is we reformulate it in very general terms. So it will be amenable to what we do. And then it will be the following thing. I have a measure space, X, and I take X cross X cross X. And the examples in question, X is a real line. However, in the course of the proof, I will have to change it. Yeah? So it might be just measure space. And later on, I explain why I don't like measure spaces. On the other hand, they're so good. Yeah, you see, measure space, the trouble with measure space, there is no such thing as a measure space. It's a contradiction in terms. Space with measure, abstract measures, are not sets. Right? They're object of category, which is not category of sets. And usually all expositions which you find in textbooks on measure theory are all wrong. Yes, mistakes or mistake or mistake. They're not rigorous. They say, oh, we believe something up to 1 point, measure 0, boom. And this is not said rigorously. I want to say it rigorously, you need the whole body of that Zermelo-Fraenkel theory, which includes sets bigger than continuum, which never you do. And of course, it's also pretty certain, usually full of mistakes. And nobody about real numbers also, yeah? Nobody ever wrote down rigorous foundation of real numbers. All known expositions have faults, gaps. We still believe it's okay, but about rigor you must be careful. Okay, but anyway, I say, given that, and then there is a subset there, and then you project it, so put it 1, 2, 3. They don't have to be the same space, yeah, they're different. And it's notationally much easier. And you have 3 reduction of that. You have omega 1, 2 in x1 times x2, and similarly omega 1, 3 in x1 times x3, and omega 2, 3 in x2, 3. And this, by the way, very good setting for entropy. So you have, and this is one way to think about entropy in physical context is as follows. Very close to what we consider, that we have a space, big space X, measure space, which is a product of xi. Maybe finite to infinite. And then we have some subset omega. And then we project it Observe, I cannot here, if I write x to the n, I cannot even write it down. Which people sometimes do in combinatorics. Ooh, it takes pages just to write it down, yeah? And you never can read it after that, right? It's very, very essential that your space is a product of not 1, 2, 3, yeah? But any set and then take subset, and then otherwise you have double indices, triple indices. I mean, horrible mess. But again, it's set-theoretic notation. They're still much more primitive than categorical notation. So you have these projections. And something is about the measures of this projection, how they relate to measure of this set. So, but in a second we see that it's entropy which matters. Actually, it's about entropies. And so the theorem says, if I take measures of this, I put a kind of brackets so it will be not confusing. I take omega 1, 2, meaning measure of that, times omega 2, 3, times omega 1, 3, and 2, 3. And this is greater or equal than omega squared. So there is this inequality. And this is a first I shall prove it and explain what it has to do with entropy and with Shannon inequality. This will be the end of the lecture today. So this is called Lummis-Whitney theorem. And it is, on one hand, it doesn't give you the sharp constant, but it is in a way stronger than isoperimetric inequality. Because if you apply it to the Euclidean space, coming back to the Euclidean space when you have omega in R3, and you have projection to 3 plane, yeah? There is 3 coordinate projection to R2, 1, 2, R2, 1, 3, and R2, 2, 3. So you have domains here, domain here, domain here, and you say, aha, this volume squared bounded by product of these areas. And this is stronger because by geometric arithmetic mean, this give you, this quantity is smaller with a proper normalization, the sum of this. Therefore, you bound this volume by the sum of this projection. But when you consider anything with domain and project it here, of course, this projection is smaller than area. Area goes down. And so up to a factor of 3, you see that this volume is less than area. Of course, you have to properly normalize, yeah? So it must be have right homogeneity. It's again, typically you don't have to write the formula. You say in principle there is inequality, and automatically you write the formula. And because formulas are shorter, people write formulas, and then they, of course, we have to decipher them back, right? And so this is a stronger modular geometric arithmetic mean. So it's for certain configuration, it's much better than isoperimetric inequality. And so all you use is this projection of geometry, what you use, that this projection area goes down, and this area is smaller than image of the projection. Right? So area of the boundary is greater than area of the projection, which is kind of obvious. Yeah? It's not deep geometry, but still this is only in geometric ingredient in this argument, and the rest is this formal abstract theorem. And this is a Lummis-Whitney theorem. And this, of course, true for any dimension. Just 3, because the first case when it is meaningless, interesting. Right? So how you prove that? So I just say 2 words, and then I'll come back to that next time. Of course, we can realize first it's kind of combinatorial problem. You can imagine this being finite set. This being just finite. This is subset, and you have this about cardinalities. So it's a combinatorial theorem in a way, but it doesn't help. Right? I say measure, I could say equally just finite sets. And this means cardinality. How you prove that? So you have this projection. You project it here, and you use kind of naturally what is called Fubini theorem, or whatever, I don't know. You just evaluate this by integrating this height. You intersect with these vertical lines. You have this domain. You integrate it, And so you have some equality. But the trouble is this kind of thing is variable. Yeah, so it's implicitly there is function involved, how these things varies. But imagine it would be constant. Then it would be very nice. You know that the total volume equals this times this height. So if you write it to all three projections, you immediately have your inequality, right? It just become A plus B equals C or something. I will reproduce it next time. But if you do it yourself, you see immediately, if you assume that your set had this property, that its projection on all three directions, all these heights, when they non-zero are equal. See, some may be zero. This is a priori subject because you have inequality rather than equality. And inequality means that some of them are secretly zero. They don't appear kind of in the picture. If you write this inequality, you immediately arrive at this inequality. So the trouble is, of course, they're far from being equal. They're all like the domain. You project it, and of course, all these intersections are different. Right? But then I'm saying, aha, and now we apply the law of large numbers. But we apply it not to your set omega, but apply it, put here number n, number n, number n, number n. The number is an infinitely large number. Here again, it's very convenient to speak in the language of non-standard analysis. So take a very, very big number, pretend they kind of, and then everything which is small compared to this disappears. Non-standard analysis, of course, is just a language, but it doesn't have much depth, but still very convenient. So, and then what I said, when n has become very large, I can imagine everything become constant. In particular, this function of this projection, when you go to the limit, it describes kind of property of isomorphism, I didn't say. All errors become, everything become constant. So the picture reduces essentially to the one which I described here, and where it's obvious. And so I have this theorem. Yeah, again, I will explain it in detail. I will explain it in detail next time. And this immediately also, if you think about that, this is a good example. Yes, you can think for yourself before listening to the detailed explanation. That first, why it is obvious when all these projections are equal, and if they only equal up to epsilon, there is epsilon error, and n goes to infinity, error goes to zero, and you have a result. Right? And this one point again, the conceptual point is you don't have to stick to one space. Yeah, you can allow anything here. It only this combinatorics of this product, how it's organized, relevant. It's not intrinsic geometry of the Euclidean space. However, interestingly enough, the corresponding sharp inequality, in Euclidean space is unknown, right? So I shall discuss a little bit. We don't know if there is similar inequality which will be fully symmetric. It's because this here extremal configuration is a cube, yeah, or rectangular solid, yeah. Probably it's actually a cube, yeah, something. It's not a ball. And how to make argument when the ball will be extremal. And there are partial results, and the proof is rather sophisticated, and it's unknown. And fully it's unknown. Though there are very closely related results which are known. So in certain reformulation of that, also quite powerful, is true for the Euclidean space. Okay, that's for today. So next time I'll repeat more or less what I started about this category and explain this in detail, the formulas which I suppressed so far.